for this test. The supposedly most severe error is that actually it was the bad case, but you declared a good case. So this is misdetection. The misdetection probability. So false alarm is sometimes called type 1 error, and this is called type 2 error. And just that there is an inherent asymmetry here. So what are we after? We are after this quantity beta epsilon PQ. It is the minimum probability of misdetection over all test such that the false alarm for that test is less than or equal to epsilon. So I want some reasonable guarantee for the false alarm. With that reasonable guarantee, what is the minimum probability of misdetection that I can give? Okay, and that's this beta epsilon PQ. It's a measure of distance between P and Q in some sense, not formally distance, but total variation distance, the one we saw earlier, is related to the error probability for the Bayesian hypothesis testing, with each of these appear with probability half. This one relates to this particular probability of error. So, and you should think of it as, and we'll soon see a result, you should think of it as kind of the multiplicative change of measure. So it's a good bound on the ratio P by Q. We'll see why I'm saying that. Okay. Okay, so this is the quantity we are after. So one basic property of this guy, and many of us know this, and I'll state it roughly. If you take IID distribution, and look at how easily can you distinguish between Pn and Qn. So this thing is, you'll see that you can design tests so that this thing goes to 0 very fast. In fact, this fast, exponentially rapidly. This limit is equal to the divergence, the Kullback-Leibler divergence between P and Q. Okay, this, if you don't know, is okay, and this is the Stein's lemma. So this is the handle that we wanted from single shot to IID case. This lemma will give us that handle. So if we give our results in terms of beta epsilon PQ for single shot, then by using sign lemma we can say something about the IID case. We'll come to it. Yeah, sorry.
What happened to epsilon?
That's right. So for all epsilon between 0 and 1, strictly less than 1. So this is like a strong converse statement that the answer doesn't depend on epsilon. The exponent remains independent of exponent of epsilon.
But epsilon is fixed, right?
It's fixed. Yeah. It's a fixed epsilon, and then we take the limit. That's right. Okay. Just the first order term. Second order term, of course, if you want to see, you'll see exponent epsilon there. Okay, so we have this lemma, and this is the basic. So now, here is the hypothesis testing problem we want to look at. My H0 is Pxyz. H1 is some conditionally independent distribution given Z. Okay. I want to use my secret key agreement protocol to design a test for this problem. So I'll run my secret key agreement protocol. It will reveal a K, a pi, and a Z. This is the view of the protocol. Of course, this is right now not practical. I'm assuming everything is available to a single guy. So the view of the protocol. This is under P. So this is the probability distribution induced on K, pi, and Z if the underlying distribution was P, X, Y, Z. Let Q, K, pi, Z be the probability distribution induced on the same protocol if the underlying distribution was this one, the useless one. Okay. So by the security criteria, we know that this distribution is approximately equal to what? right. So it's approximately equal to uniform times p pi z. Okay, that's the knowledge we want to use. So we can try this proof. It doesn't. We can try to do something with this knowledge, but it doesn't go through immediately. So there's a little trick we need. What is that trick? We need to introduce a new security criteria. It's already there in literature. So right now we had a recoverability condition and a security condition. We would like to combine them into a single condition which captures both. What is that single condition? So forget about the k. I'm defining an epsilon secret key with one single condition in the following manner. Suppose I have the estimate kx, ky of the key. I have this transcript and I have z. This is what's happening in the real world. What do I want in the ideal world? In the ideal world, I want a uniform distribution over a diagonal. So think of this. This is a distribution over kx comma ky, and this is 1 if both are equal divided by k. That's like saying it's a uniform over a diagonal. So I want this distance to be less than equal to epsilon, and I'll call such a kx ky an epsilon secret key. This is a new definition. It combines recoverability and secrecy the way we had it into a single thing. So just a small remark, an epsilon secret key in this sense implies an epsilon secret key in the previous sense, and an epsilon delta secret key in the previous sense, an epsilon delta secret key in the previous sense implies an epsilon plus delta secret key in this sense. You can show this, very simple. So this is a new definition, almost the same as the previous one, which had recoverability and secrecy separate. But I got rid of my k. If you see, there's no k now. I'm talking directly about the estimates kx and ky, and I want the estimates themselves to be close to a uniform distribution over a diagonal. Okay. So I have this definition of secrecy now. So now maybe I can compare p kx ky pi z and q kx ky pi z. This one I know is close to this distribution. It's the uniform distribution over a diagonal. Please pardon all the notations. What do I know about this one? Is there a form I have for this one? Here is a nice observation which is well known and has been rediscovered several times. If you start with independent random variables and condition them on interactive communication, they remain independent. Okay? You can't build up correlation by interactive communication. So independent random variables remain independent when conditioned on interactive communication. So condition on z, x and y are independent. Then conditional additionally on pi, they remain independent. So this distribution has this nice form. Okay, that's the form of this distribution. And now, so this is approximately equal to delta. I'll construct my test with this, and it will work well for this one because they're not too far. I'll be off by delta. Oh, sorry, I'm calling it epsilon. Sorry, epsilon off. This epsilon now is epsilon plus delta because of this result. Okay, so we have these two distributions. What is my test? I'll define just the acceptance region. So when would I accept the null hypothesis? If I have kx, ky, a transcript t and z, such that if you look at log, a very simple test of indicator function kx equal to ky. So if you look at this guy, it's more than some threshold lambda. And what is my, so it's a threshold test. This is the region in which if I get something here, I'll declare this is the good case. This is what we'll call the acceptance region. If I get something here, I'll declare the good case. Okay, and this lambda is an extra parameter I want here. I think eta, but this lambda eta is just the first parameter I need. It's no big deal. I think this I have to quickly check. Don't want to make a mistake. K by eta maybe. Okay. Threshold is 0. What is my threshold? 2 by k. Eta square k maybe, yeah. I think it's this. Shun can correct me. Okay. I think this is just a threshold I'm choosing. Now, what is the point of choosing this threshold this way? You can see that for this particular test, you can very quickly analyze the misdetection probability. It's the probability that you're counting things under Q, but it was actually P. But we have a handle over replacing Q with some other distribution, this one here. And you do that measure change argument, and you can just show that this is less than equal to k inverse by eta square. Yeah. I'm allowing more flexibility, but how it's just some arbitrary Q here. So I don't have any handle over Q pi z as such. You can choose anything here. So I'll give a bound in which you'll have this Q as a parameter over which you can optimize later on, and it will help you maybe.
I think I'm failing to capture the meaning of the test.
Test is, this is the good distribution. How far is it from an independent distribution which is completely useless?
Okay, that's true, but shouldn't you still keep the pi and the same for that?
I can't ensure that because pi comes from your protocol. I can only define this distribution. But the good thing is once you define this distribution, whatever pi k z is, it will always have this form. Given pi z, it will be independent here. So yeah, I'm not defining a distribution on k pi z, I'm defining a distribution on the observations. And then this is the induced distribution on because of your protocol, which you are giving me. And I'm saying whatever protocol you give me, I'll use it to distinguish between those two cases because I can distinguish these two things. Okay, that's the reduction argument.
I guess I'm confused because it looks like you're taking the ratio of the two to define your test.
Right, test for this and this for now. For now, this and this. But if I define a test for this and this, okay, maybe it's a good point to just say this thing.
This z is not that z. This is just some generic z. You're using pi z as z.
No, these two are just the same, exactly the same z. So
you're using the pi z as the z.
no, this is the original distribution on x, y, and z. And then you run the protocol. Now what do you get out of the protocol? Kx, ky, pi, but z also. So
You're apparently seem to be using this result there with the pi z there.
I have not used this result yet there. It's just I want.
Viewpoint, let's say. You're using it with the pi z playing the role of this z.
No, that's not. So I start with these distributions, and this inducer distribution on kx, ky, pi, and z. The marginal of z remains fixed. It's the same thing from here, but it's the same z from here.
But then when you apply it there, you're thinking of pi z as being a new z apparently.
I'm not. This is pi z. This is pi and z. It's not a new. It's the original z. This
Pi z is the original z.
no. The z was the side information given to the eavesdropper. Pi z is that side information plus the communication. These are the original measures. This is after the protocol is done. This pi z is. Oh, you are saying? Is it a heuristic argument you're making that I'm? No. This.
This
Okay.
is all kind of happening inside your hypothesis test.
Right.
Protocol and generating pi from the given x, y, and z.
Right. So you are given these distributions. You run your protocol. You observe kx, ky, pi, and but z also. Z was already there as a parameter available to the eavesdropper. So this is a view which it's not available to single party. Collect all the things together. And this is what you're saying. Now you want to use this to distinguish what was the case here.
So why do you keep independence when you run the protocol?
This part here, right? So this is the result I am just using, that if you have independent distribution and you condition them on interactive communication of x and y, it remains independent. Okay. It needs a proof. It needs a proof. Yeah. It needs a proof. So one way to show this is if you have x and y which are, and you condition them on an interactive function of x and y, then this inequality holds. You can show this. So if this was 0, then this must be 0. So if they were independent, then they remain independent. So this you can show. It needs a proof. It's a cute observation, but it's well known. So for some people, so not for me. So I didn't do the proof. Okay.
Can you show me parse what this A exactly means in its notation?
Sorry.
Can you parse this A?
Okay. A is the acceptance set where if I get something here, I'll accept the null hypothesis. Tau is my transcript. Yeah. So kx and ky are key values. Tau is the transcript realization, and z is the eavesdropper observation. So when I run the protocol, what do I observe? I observe a transcript, communication transcript. I observe keys which I have agreed on, and I observe the eavesdropper observes a z. This is all that observations, and I just use a very simple threshold test with those observations.
With respect to the probability that it appears in Q?
Yeah, so I know the Q here, so and I know the protocol, so I can evaluate this distribution. It's not a practical scheme, but you can evaluate it. So you evaluate this distribution, and this distribution is very simple to evaluate. Just indicate a function by cardinality of k. Take the log likelihood ratio. If it's more than a threshold, I accept. If it's less, I reject.
And the 1 simply means it's a predicate in that sense.
Yeah, 1 means that it's 1 if this are equal and 0 otherwise. So if they are 0, if kx is not equal to ky, then I immediately reject. So, okay, so you can show this, and you can also show this. I think this one requires proof. It's slightly involved, but this is less than epsilon plus delta, or in this case just epsilon plus eta. Epsilon is the distance between this and this guy. Okay, so you can show these two things. So what have we attained? We have attained a test with probability of false alarm less than equal to epsilon plus eta. I'm skipping proofs here. Okay, this one requires work. And false alarm less than equal to this, which relates to the size of k. So this things imply that beta epsilon plus eta for p x y z and let's say q x y z are original q of that form is bounded above by this guy here. So I'll move to that side. So here is the bound that we were after. We have shown that no matter what protocol you use, the key that you generate is no more than minus log beta epsilon of p x y z q x y z plus some small beta epsilon plus eta maybe plus some small 2 log 1 over eta, and you can choose any eta you want. But this is just don't forget about this part. That's what we have shown. So any key that you generate cannot be of length more than minus log p x y q x y, because we came with a test with false alarm less than equal to epsilon plus eta, and misdetection related to the key length. So the longer the key, smaller is the misdetection probability. Okay, so the log of the key length relates to the probability of false alarm. And that's the bound we were after. This is what we'll call what we were calling the conditional independence testing bound. So
This is true for any Q.
this is true for any Q of independent form.
Can you attribute it just so I know where to look?
Okay, right. So just a small history. There are converse results in channel coding which are based on reduction to hypothesis testing. There's an early version of that result in a book by Nagaoka, which Professor Hayashi pointed me out to. But recently there's a paper, quite popular paper by Polyansky, Poe and Verdu, which does this reduction of channel coding to hypothesis testing and gets some implications of it. So this is a paper which appeared, at least this bound appeared in Eurocrypt 2014. And there's a subsequent journal version in IT Transactions which came out last year, which gives this reduction when you even have hypothesis, when you have interactive communication. And for the secret key problem, a slightly different problem than channel coding problem. So that's where it appears. So what do we get out of it? Well, you can choose Q to be the one coming from marginals of Px and Py now. So it can be Px given Z, Py given Z, and Pz. And then use, for ID distribution, use Stein's lemma to immediately get an upper bound of I of xy given Z. So this is, I'm stopping here, so I'm rushing. So it says that C epsilon, this epsilon was my proxy for epsilon plus delta now. So it says C epsilon plus delta x, y, z is less than equal to, by Stein's lemma, you get divergence between this and the marginal p. That divergence turns out as mutual information. And this upper bound holds irrespective of what epsilon and delta is, as long as epsilon plus delta is strictly less than 1. Okay, so for instance, when z is constant, this is mutual information between x and y. So what we have shown is that the result with which Maurer and Alswida-Chisar had holds even if you allow epsilon plus delta to be arbitrary, but strictly less than 1. So this is what we'll call a strong converse for the secret key capacity. That's one implication. You can do other things with this bound. You can in fact apply this bound for data compression problems. That's another line we won't cover. But Shun will do some applications of this bound for the secure computing problem. But the bound is simple. It relates the key length to this binary hypothesis testing exponent between P xyz and Q xyz, and you are free to choose Q xyz. This helps. In IID case, it doesn't help that much. In single shot case, sometimes it's convenient to choose a suboptimal Q xyz just to give a tractable bound. Okay? But that's where I wanted to stop, and now Shun will take over. Yeah. Yeah, so that's the point. If you do single shot, or if you do finer things in the first order thing, then you won't use Stein's lemma. Maybe you use some other better bounds than Stein's lemma. You can also use alpha order Rényi divergence, which showed up yesterday here. It is also related to this guy. So there are many bounds known for beta epsilon. Mainly they are popular these days because of the meta converse of Polyansky, Poe and follow-up work. Professor Hayashi has made some fundamental contributions there. I mean, so there is, the good thing is we know a lot of bound for this guy. They are there in literature, and so we can pull up all these bounds and say something at finite length. And for two parties, we have a separate paper where we could do more refined evaluation, and these bounds are not too bad. Around n equal to 100,000, they become very close to each other. I mean, if we gave an achievability, we gave a converse. Not that achievability, some other achievability, which probably Shun will cover. We can show that at n equal to 100,000, we are very close. At n equal to 1,000, we are not close, but still better than the capacity bound for sure. So you can simulate these bounds and check how good they are. That's another advantage. Okay, that's all I want to say.
So in this second part, I'm going to cover this secure computing problem. Because we are slightly run out of time, so probably I'll only cover oblivious transfer. But if I have time, I'm going to cover bit commitment. So I'm going to review some basic results on secure computing. In particular, so in problem formulation, this secure computing problem looks quite different from a secret key agreement problem. But actually, there is some intimate relationship between secure computing and secret key agreement. And so I'm going to explain that. And then we use this bound on the length of secret key agreement. And we are going to get some impossibility bound on secure computing problem. Okay. So this is the plan. Okay, so what is secure computing problem? So secure computing problem was introduced by Yao in his seminal paper in '82. And so there are two parties. And they have some data, U and V. And they would like to compute some function, Z1 of U and V. Z2 of Z2, U and V. Okay? And so these functions may be the same or maybe different. So they would like to compute some functions by using some interactive function, interactive communication. So they would like to compute some function, but they don't want to reveal their own data. So this is the problem. For example, in the Millionaire Problem posed by Yao. So there are two millionaires. They are very rich, and they would like to compare the amount of their fortune. They would like to compare the amount of their fortune, but they don't want to disclose the exact amount of their fortune. They just want to compare which is larger, something like this. So more formally, we can define the security of this secure computing problem like so. By using these two Markov chains. So this means that this communication does not reveal about V, does not reveal more information than this function value and the observation U reveals about V. And the same for this guy. So so this is the goal of secure computing problem. And so this is a secure computing problem for general function. And particularly important function is called oblivious transfer. So what is oblivious transfer? So for oblivious transfer, there are party 1's observation is two binary strings of length L, and second party's observation is just single bit. So we have some black box oblivious transfer, and they input these observations. And the output of first party is nothing. So and the output of the second party is one of these sequences that is specified by the input of the second party, so K of B. And this K of B complement should be kept secret from the second party. And this B should be also kept secret from the first party. So this is oblivious transfer function. So this oblivious transfer function looks a little bit strange at first glance, but it is known that so if we can realize this oblivious transfer, we can realize secure computing for any function. This is known. Oh, by the way, this oblivious transfer was introduced by Rabin in 81 and independently by Evan Goldreich, Lemper in 85. And so there is a famous reduction technique proposed by Killian in 88. So he showed that if we can realize this, we can realize any secure computing for any function. His reduction is quite complicated, but to get some idea, I'm going to show one example how we use this oblivious transfer to compute some another function. So suppose that so party 1's observation is binary string of length L, and party 2's observation is just single bit. And party 2 would like to compute some function g of u and v. Okay. So how do we compute this g of u and v by using this oblivious transfer? So so the scheme is the following. So because party 2's observation is just binary, so there are two possibilities. So party 1 first pre-compute g of u and 0 and g of u 1 locally, and input this to this oblivious transfer. On the other hand, second party input v, v to this oblivious transfer. Then this oblivious transfer automatically output on this side nothing, and on this side automatically output g of u and v. So this is rough idea how we use oblivious transfer to compute some other function. So pre-compute at one end and use oblivious transfer. Yes.
Quick comment. What you're doing is semi-honest security, because you're expecting the first party to feed that there is a value u for which those two values are g0 and g1. If you're just doing semi-honest security, actually something much simpler than creating this.
What security?
Semi-honest.
Semi-honest. Yes, yes.
So this is semi-honest.
This is semi. Oh yes, yes. So.
Killian is kind of just something much simpler than create that's possible along the lines here.
Okay. Okay. Thank you very much. Oh, by the way, so today's talk is all about semi-honest case. So the parties are curious to know the other party's input, but they follow the protocol. They do not deviate from the protocol design. Okay.
Why is there no reference to the transcript in this discussion?
This scheme?
No, in this whole discussion, somehow the concept of a transcript doesn't seem to enter.
Oh, that will appear in a few minutes.
So this notion of a cross involves the transcript. Yeah, the OT box there. No, but the cross on the thing that you're not supposed to know is supposed to involve the transcript.
Oh, okay. So this is black box, and now I'm going to explain how we realize oblivious transfer, and then their transcript will appear.
The meaning of the cross, perhaps, is somehow involves the transcript. To not know B must somehow involve the transcript.
You're knowing something you don't know.
Oh. Yeah, no. To realize oblivious transfer, they communicate. But this is just black box, so it looks like there is no transcript. But to realize this, you need communication, of course. Yes?
This is incoming theoretic security after this point. This is reduction is
this reduction is, reduction is information theoretic, yes. Yes, not computational. So this is oblivious transfer. So if we have oblivious transfer, we can compute any function we want. Information theoretically secure oblivious transfer cannot be realized from scratch. So we consider the problem to realize this oblivious transfer from some correlated source, x and y. So the parties observe correlated source x and y, and so party 1 also observe L binary sequence of length L and one binary bit, and they communicate. And at the end of the protocol, so party 1 get nothing, and this B should be kept secret from the first party, and party 2 would like to get K of B, and this KB complement should be kept secret from the second party. So this oblivious transfer from correlated source, some resource, was initially studied by Klepo-Killian in 1990, and later more Shannon theoretic formulation and some capacity result was studied by Nascimento, Winter, in 2008. Conference version appeared a little bit earlier, but journal version is 08, and also by Alfred Tisser. In conference version appeared 07, I think, and the journal version appeared in 2013. Okay. Okay, so this is oblivious transfer from correlated source, and I'd like to define formal definition of this problem. So how do we define? So we have three parameters: epsilon, delta 1, and delta 2. So first requirement is reliability. So at the end of the protocol, the second party will get some estimate on K of B, which I denote by K hat. So this K hat, the disagreement probability of K hat with KB should be smaller than epsilon. This is reliability condition. And K hat is the estimate of the second party, estimate on K of B. Given Y and I and B. So security for the first party. Yes.
X, Y are independent of everything, K0, K1.
Yes, X and Y. So this resource X and Y are independent of K0, K1, and B. Okay, so they have some independent resource, and they implement oblivious transfer by communication.
Sorry, so what does that mean? So you have a joint distribution on K0, K1, and B?
Oh, K0, K1 is just independent two binary string. Let's say it's uniform. And B is also independent uniform binary bits.
Why do you assume any distribution on the input?
Excuse me?
Why do you need to assume any distribution on the input?
We're doing randomized Oblivious Transfer.
Oh, it's uniform. Uniform assumption of uniformity is not that important to make it simple, just assume. But yeah.
It's easy to, I mean, it's easy to convert, honest, but here it's better.
Yeah. Yeah.
Independence seems kind of critical, right? K0 independent of K1 seems a bit weird.
K0 independent of K1 is, yeah, that's important. But so if we can realize this, then we can implement some other cases. So this is the most basic primitive. Any other
You
question?
still can implement, like, so if you remove the restriction of the uniformity, you still probably can get a secure OT for the case where the adversary chooses K0 and K1 depending on X, right? So X needs to be independent of the uniformity.
K0, K1 must be.
So X needs to be independent of K0, K1.
Yes. That's crucial assumption. Yes, of course. Okay. So yes. And so what is security? Security for party one. So security for party one is the following. So so in Oblivious Transfer, party two should only get K of B, and K of B complement must be kept secret. So we evaluate this by using variational distance. So probability distribution of KB complement Y, B, and transcript should be close to this independent distribution within delta 1. Okay. So this is view of party 2, by the way. And similarly, we have security for party 2. So what is this? So so this B should be kept secret from the first party. So the joint distribution of B, K0, K1, X, I should be close to so this is view of party 1. Okay, so if the protocol satisfies these three conditions, we say that that protocol realizes epsilon delta 1 delta 2 Oblivious Transfer.
Shouldn't KB also play a role in your security for party 1 somehow? I mean, it's
K of B.
I mean, somehow it's just throwing away the K of B because everything is conditioned in your joint
This one?
model, right?
K of B. Oh,
So somehow it's got to enter the definition because if everything has got some arbitrary joint distribution, throwing it away seems bizarre.
Party 2 sees Y.
party sees this is all the information party 2 gets.
Yeah, but somewhere
Yes.
in the background, the KB is sitting around, which is conditioning the whole picture.
Why do you condition on KB?
You know what I mean? The variables in this probability model also involve the KB.
Yes.
So you're just studying something at some marginal level where you've sort of averaged out over the KB, which is strange.
First condition is KB.
Yeah, so first condition involves KB, and these conditions should be defined for marginal, I think.
No, there's, I mean, there are all these variables around, so there's also this other variable, which is the K sub B. So it just seems to me that this definition of security could be strengthened in some way.
Why could you include it?
Is that?
Why could you include it? Why?
Well, why not? I mean, that's a matter of decision.
Yeah, so this is a requirement. So this KB complement must be kept secret from party 2, and B must be kept secret from party 1. And there is no constraint on KB.
But for certain sense, if K0 is equal to K1, then knowing KB, I know KB complement, right?
So the reduction that you can have K0, if the assumption that K0 or K1 is independent, you can remove that by reduction.
But then I guess we have a different security definition.
Yes, yes. Oh, 5 minutes? Okay. Excuse me? Bees, yeah. Yes. Uniformity of KB is second length. KB complement must be kept secret in the second. Okay, so sorry. This is yes. This is KB complement. Sorry. Yes, KB complement. Sorry, this is. Yeah, I should write this a little bit larger. Sorry about this. So yes, KB complement must be kept secret, and B must be kept secret, and we evaluate this by this variational distance. Oh yes.
So I guess some of the questions were, and you also said that you're just going to restrict attention to honest but curious.
Yes.
Can anything be done against
malicious case?
adversaries?
Yes, there are some results on malicious adversary, and in the case of malicious adversary, the security definition for the first party will be slightly different. So if the second party is malicious, he tries to get information for both KB and KB complement. So in that case, we require that there exists some B prime that is generated by the second party's observation, such that I think this is the definition. So if the second party is malicious, there is no guarantee about KB complement anymore, because, for example, instead of estimating KB, party 2 can try to get KB complement, right? By pretending the observation is B complement. So there is no guarantee for the concealing about KB complement, so we require that at least one of them must be kept secret. So KB prime must be kept secret. So this is the condition for malicious case.
This reminds me a bit of in the computational world. People look at like kind of indistinguishability-based definitions of security. Like there was some Micali, Haas, Rosen paper on input indistinguishable secure computation, or computational setting.
Yes.
But usually the preferred definition is a simulation-based. Can one, is this equivalent to some kind of simulation-based definition with a undone simulator?
The views we are listed is measured by this way. So in other words, we allow the distinguishability when you do
the simulation based, the person who's trying to distinguish is all powerful. Can do any possible statistical test.
I can comment. So you're asking for the malicious case, right?
Yeah.
So there's a paper by Kappa and Buchman where we give a simulation-based definitions for standalone security, not QC security, and they show its equivalence. It's an unbounded simulator.
Yeah.
So yeah, it could give a list of conditions. Not exactly these; they have their own similar conditions.
But, but in this definition, you don't require that party one knows the input, for instance.
What's it?
That party one knows the input.
So that there, the definition is if party one is correct, yeah, here they extract their inputs, right? So they give a.
But this is not the definition.
This is not the definition. It doesn't talk about the party one being malicious here. But the other definition makes sense.
Okay. Should I stop somewhere and should we take break or? Maybe, yeah, or we defined, so maybe this is the right place to take a break.